welcome to this problem walkthrough. Today, we will be exploring problem number 347, top k frequent elements. This is a fascinating problem that combines elements of frequency counting, sorting, and optimization. We'll break it down step by step, exploring different approaches and their complexities. Let's get started. The problem we're solving is called top k frequent elements. You're given an array of integers, nums, and an integer k. The task is to return the k most frequent elements from this array. The key thing to note here is that the order of the elements in the output does not matter, meaning as long as the top k elements are correct, their arrangement is flexible. For the input, you're provided with nums, which is the list of integers, and k, which specifies how many of the most frequent elements you need to return. The output, in turn, will be a list of integers representing these top k elements, again in any order. To make this clearer, let's dive into some specific examples. In the first example, the input is nums equals 1, 1, 1, 2, 2, 3, and k equals 2. The output is 1, 2. Here's why: if we count the occurrences of each number in nums, the number 1 appears 3 times, 2 appears 2 times, and 3 appears just once. Since we need the top 2 most frequent elements, the result includes 1 and 2. Notice that the order of these elements does not matter, so 2, 1 would also be a valid output. Now, consider the second example where nums equals 1 and k equals 1. In this case, the array contains only one element, 1, which is of course the most frequent. Because k equals 1, the output is simply 1. Now let's look at another example. Here, the input is nums equals 4, 4, 4, 6, 6, 7, and k equals 1. The output is 4. Breaking this down, we see that 4 appears 3 times, 6 appears 2 times, and 7 appears just once. With k equals 1, we are looking for the single most frequent element, which is 4. Therefore, the output is 4. These examples highlight how the problem focuses on counting the frequencies of elements in the array, ranking them, and then selecting the top k based on their frequencies. The order of the elements in the output remains flexible, as long as the correct k elements are included. To wrap up the problem statement, let's review the constraints and edge cases. First, the length of the array nums will range from 1 to 10,000, and each element in nums will lie between -10,000 and 10,000. The value of k will always be at least 1 and at most the number of unique elements in nums. For edge cases, consider when nums contains only one element, such as nums equals 5 and k equals 1. Here, the output is simply 5. Another case is when all elements are unique, like nums equals 1, 2, 3, 4, with k equals 2. In this scenario, any two elements can form the output, such as 1, 2, or 3, 4. The algorithm should also handle negative values, such as nums equals -1, -1, -2, -2, -3, with k equals 2, where the output would be -1, -2. Finally, if multiple elements have the same frequency, their order in the output doesn't matter, aligning with the flexibility in the problem's requirements. To solve the problem of finding the top k frequent elements, one straightforward approach is the brute force method. Here, we begin by counting how often each element appears in the input array using a dictionary or hash map. Once we have the frequencies, we sort all the elements in descending order based on their frequency. Finally, we select the first k elements from the sorted list. While this method is simple and easy to implement, it has a significant drawback. The sorting step dominates the runtime, resulting in an overall complexity of n log n. This can become inefficient, especially for large arrays or when k is small compared to the input size. Sorting all elements is excessive since we only care about the top k, making it clear that we need a more efficient strategy. A more efficient method involves using a heap to optimize the process. Instead of sorting all elements, we can use a min heap to track only the top k frequent elements. First, we count the frequency of each element with a hash map, which takes n time. Then, we maintain a min heap of size k. For each element, we add it to the heap, and if the heap exceeds size k, we remove the least frequent element, which ensures that only the top k elements remain. Each heap operation takes log k, and since we repeat this for all elements, the total time spent on heap operations is n log k. This approach significantly reduces the complexity compared to sorting, particularly when k is much smaller than n. However, managing the heap introduces some additional memory and computational overhead. An even more optimized approach leverages the fact that the maximum frequency of any element in the input is bounded by the array size, n. This allows us to use a technique called bucket sort. We start by counting the frequency of each element using a hash map, which takes O(n). Next, we create an array of buckets, where the ith bucket contains all elements that occur exactly I times. Once the buckets are built, we traverse them in reverse order, starting from the highest frequency, and collect elements until we have gathered the top k. Since both the bucket creation and traversal are linear operations, this approach achieves an overall time complexity of O(n). It is highly efficient, but it does require additional space to store the buckets. After analyzing the different approaches, we have chosen the optimized bucket sort strategy. There are several key reasons for this decision. First, sorting all elements with the brute force approach is wasteful since we only need the top k, and its O(n log n) complexity is unnecessary. While the heap approach is more efficient, with O(n log k) complexity, it still involves some overhead, particularly when k is large relative to n. The bucket sort, on the other hand, takes advantage of the fact that frequencies are bounded by the input size, enabling us to achieve linear time complexity. This realization was a turning point, as it allows for a direct and efficient way to retrieve the top k frequent elements without unnecessary computations. The simplicity and scalability of bucket sort make it the best fit for this problem. When comparing the trade-offs, each approach has its strengths. The heap-based method is advantageous in scenarios with tight memory constraints, as it does not require additional space proportional to the input size. On the other hand, bucket sort is ideal for time-critical applications, as it minimizes runtime with its linear complexity. The brute force method, while simple, is not practical for large inputs due to its O(n log n) complexity. Ultimately, we selected bucket sort for this problem because it strikes the right balance between efficiency and clarity. It meets the problem's requirements, scales well for large inputs, and ensures fast execution, making it the most suitable choice overall. The problem asks us to find the top k most frequent elements from an array. For instance, if you are given an array of integers nums and a number k, your goal is to determine which elements appear most frequently and return exactly k of them. To achieve this, we can break our approach into several steps. First, we count the frequency of each element in the array. This is important because identifying the most frequent elements requires us to know how often each number occurs. We can do this efficiently using a hash map, where each number is stored as a key, and its frequency as the corresponding value. To populate this hash map, we iterate through the array and increment the count for each number as we encounter it. Once we have the frequencies, the next step is to organize the elements by their frequency. By grouping numbers based on how often they appear, we can quickly access the ones with the highest frequencies. To accomplish this, we use a bucket sort approach. Here, we create a list of buckets, where the index corresponds to a frequency, and each bucket stores the numbers with that frequency. For example, if a number occurs 3 times, it will be placed in the bucket at index 3. Iterating through the hash map, we append each number to the appropriate bucket, building an efficient structure to process the results in the next step. After organizing the elements into buckets, we need to collect the top k most frequent elements. Since the numbers with the highest frequencies are stored in the buckets with the largest indices, we start from the last bucket and work our way backward. As we traverse the buckets, we collect numbers from the non-empty ones until we have exactly k elements. This process stops as soon as we reach the desired count, ensuring that we don't perform any unnecessary computation. A few key insights make this approach efficient. First, using a hash map for frequency counting allows us to perform insertions and updates in constant time, leading to an overall time complexity of O(n) for this step, where n is the size of the array. Second, the bucket sort approach eliminates the need for traditional sorting. Since the maximum frequency of any number cannot exceed n, the number of buckets is also limited to n. This ensures that we avoid expensive O(n log n) operations, making the process highly efficient. Once the numbers are organized into buckets, we can efficiently collect the top k elements. By iterating through the buckets in reverse order, starting from the highest frequency, we directly access the most frequent numbers first. This ensures that we gather the top k elements in optimal time without redundant processing. The data structures used play a crucial role in this algorithm. First, the hash map allows us to count frequencies in O(n) time. Here, the keys represent the unique numbers in the array, while the values store their respective frequencies. Second, the bucket list organizes these numbers based on their frequency. Each index in the list corresponds to a frequency, and the buckets contain the numbers that occur with that frequency. For example, if the input array is 1 1 1 2 2 3, the hash map would count the frequencies as 1 3 2 2 3 1, and the bucket list would look like 3 2 1. In this structure, index 3 stores the number 1 because it appears 3 times, while index 2 holds 2, which appears twice. This design ensures that we can efficiently retrieve the most frequent elements. Now let's analyze the complexity of this approach. The time complexity is O(n). Breaking it down, counting the frequencies using the hash map takes O(n), since we iterate through the array once. Distributing the numbers into buckets also takes O(n), as we process each number and its frequency exactly once. Finally, collecting the top k elements involves iterating through the buckets, which also takes O(n), in the worst case if we traverse all the buckets. Therefore, the overall time complexity remains linear, O(n). The space complexity is also O(n). This is because we use a hash map to store the frequencies, which requires space proportional to the number of unique elements. Additionally, the bucket list uses space proportional to the length of the array, as the maximum number of buckets is equal to the array size. Thus, both time and space complexity are optimized for this problem. Let's walk through a concrete example to see the algorithm in action. Suppose the input array is nums equals 1 1 1 2 2 3 and k equals 2. First, we count the frequency of each element using a hash map. The result is 1 3 2 2 3 1, where 1 appears 3 times, 2 appears twice, and 3 appears once. Next, we organize these numbers into buckets based on their frequencies. The bucket list becomes 3 2 1. Here, index 3 contains 1, since 1 occurs 3 times, index 2 holds 2, and index 1 contains 3. Finally, we collect the top k elements. Starting from the last bucket, we add 1 from index 3. Moving to index 2, we add 2. At this point, we have collected 2 elements, which is our target k. Therefore, the output is 1 2. This example demonstrates how the algorithm efficiently identifies the top k most frequent elements using frequency counting, bucket sort, and optimal collection. This Python implementation solves the top k frequent elements problem using a combination of a frequency map and a min heap. Here's a line-by-line breakdown. 1. Imports. The counter class from the collections module is used to count the frequency of elements, and the heap module is used to manage the min heap. 2. Step 1. The counter nums function creates a frequency map, which is a dictionary where keys are the unique numbers in nums and values or their respective frequencies. 3. Step 2. We define an empty list called heap. This will serve as a min heap to store the top k elements as tuples of frequency element. Using the heap module, we push each frequency element pair into the heap. If the heap size exceeds k, we remove the smallest, least frequent element using heap.heappop. This ensures the heap always contains only the top k most frequent elements. For step 3, after processing all elements, the heap contains the top k elements. We extract these elements from the heap into the result list using heap.heappop. Since the heap is a min heap, elements are popped in ascending order of frequency, thus, the order of elements in the result is arbitrary. 5. Return. Finally, the result list, which contains the k most frequent elements, is returned. The result can be in any order, as the problem does not require a specific order. This approach is efficient and works in n log k time, where n is the number of elements in nums and k is the number of top frequent elements to return. The frequency map construction takes n, and maintaining the heap of size k during the iteration takes n log k. Here, we start by defining a method called topkFrequent that takes an integer array nums and an integer k as input. The goal is to find the top k most frequent elements in the array. First, we build a frequency map using a hash map to count how many times each number appears in nums. For each number in the array, we either add it to the map or update its count using the getOrDefault method, which simplifies the process. Next, we use a min heap, implemented as a priority queue, to keep track of the top k elements based on their frequency. The heap is structured so that the element with the smallest frequency stays at the top. As we iterate through the frequency map, we add each entry to the heap. If the size of the heap exceeds k, we remove the smallest element to ensure we only keep the top k elements. This approach ensures efficiency while managing the heap size dynamically. Finally, we prepare the result array to store the top k frequent elements. Using a while loop, we extract elements from the min heap one by one. Since the heap stores elements as arrays where the frequency comes first and the number second, we retrieve the number at index 1 for each entry and add it to our result array. We increment the index as we go, ensuring that all top k elements are added in order. Once the heap is empty, we return the result array as the output. This completes the implementation, providing an efficient way to solve the problem using a combination of a frequency map and a min heap. Let's start by considering the example where the input array is nums equals 1, 1, 2, 2, 2, 3, and we need to find the top two most frequent elements. The first step is to count the frequency of each number using the counter class. This gives us a frequency map, 1, 2, 2, 3, 3, 1, meaning the number 1 appears twice, 2 appears 3 times, and 3 appears once. Next, we initialize an empty min heap, which will help us track the top k frequent elements efficiently. Then, we push each element from the frequency map into the heap in the form of frequency number pairs. For example, we first push 2, 1 into the heap, followed by 3, 2, and 1, 3. At this point, our heap contains 1, 3, 3, 2, 2, 1, because heaps are organized by minimum frequency. Since the heap size exceeds k, which is 2, we remove the smallest element, leaving us with 2, 1, 3, 2, as the heap's final state after this step. Now that we have the heap containing the top k frequent elements, the next step is to extract these elements. We pop the elements from the heap, which gives us the numbers in order of increasing frequency. Starting with an empty result list, we first add 1 to it, then 2. The result list is now 1, 2. To ensure the result is in descending order of frequency, we reverse it, which gives us 2, 1. This is the final output for the first example. Shifting to another scenario, consider an edge case where all elements of the input array nums equals 4, 5, 6, 7 have the same frequency and we need the top 2. The frequency map in this case is 4, 1, 5, 1, 6, 1, 7, 1, indicating that each number appears exactly once. We again start by initializing an empty heap. With the frequencies calculated, we now push each element into the heap. First, we add 1, 4, resulting in heap equals 1, 4. Then, we push 1, 5, which updates the heap to 1, 4, 1, 5. Next, 1, 6 is pushed, making the heap 1, 4, 1, 5, 1, 6. Since the heap size exceeds k, we remove the smallest element, leaving 1, 5, 1, 6. Finally, we push 1, 7 into the heap, resulting in 1, 5, 1, 6, 1, 7. Again, we remove the smallest element to maintain the heap size of k, so the heap becomes 1, 6, 1, 7. From here, we extract the top k elements. Popping from the heap gives us 6, then 6, 7. Reversing this list, if needed, results in 7, 6, which is our output for this case. Finally, let's look at an example with a larger k value, where the input is nums equals 1, 1, 1, 2, 2, 3, and k equals 3. The first step is to calculate the frequencies, giving us 1, 3, 2, 2, 3, 1. With this frequency map, we initialize an empty heap. We then push each element into the heap as frequency number pairs. First, 3, 1 is pushed, so the heap becomes 3, 1. Next, 2, 2 is added, resulting in 2, 2, 3, 1. Finally, 1, 3 is pushed, making the heap 1, 3, 3, 1, 2, 2. Since the heap size is equal to k, no elements are removed at this stage. To extract the top k elements, we pop from the heap, which gives us 3, then 3, 2, and finally 3, 2, 1. Reversing this list, if needed, gives the final result 1, 2, 3. This completes the walkthrough for the given examples. Here, we start by analyzing the time complexity of our solution, which is broken down into 3 key steps. First, we count the frequencies of the elements in the input list nums. By using the counter class, we perform a single pass through the list, making this step O, n, where n is the length of nums. Next, we build a min heap to maintain the top k frequent elements. For this, we iterate over the unique elements in the frequency underscore map, represented as U. Each insertion or removal in the heap costs O, log k, and since we perform these operations at most 2 asterisk u times, this step results in a complexity of O, u asterisk log k. Finally, we extract the top k elements from the heap. This involves performing k heap pop operations, each costing O, log k, leading to a complexity of O, k asterisk log k. Together, these steps form the foundational components of our time complexity analysis. Now, we calculate the overall time complexity by summing up the contributions of all 3 steps. The total cost becomes O, n, plus O, u asterisk log k, plus O, k asterisk log k. In the worst-case scenario, where each element in nums is unique, u equals n. Substituting this, the complexity simplifies to O, n plus n asterisk log k plus k asterisk log k. Since k is typically much smaller than n, the dominant term is O, n asterisk log k, and so the final time complexity for this solution is O, n asterisk log k. Shifting to space complexity, we analyze the memory used in each step. The frequency map requires O, U, space, which is at most O, n, in the worst case. The min heap stores up to k elements, taking O, k, space, and the result list for the top k elements also takes O, k. Therefore, when combining all these components, the total space complexity is O, U, plus O, k, which simplifies to O, n, in the worst case. When we summarize the total space complexity, it is O, U, plus O, k, as calculated from the frequency map, heap, and result list. In the worst-case scenario where all elements in nums are unique, u equals n, leading to a final space complexity of O, n. Comparing this with a brute force approach helps highlight the efficiency of our optimized method. A naive implementation would involve counting frequencies in O, n, sorting the unique elements by frequency in O, u asterisk log u, and selecting the top k elements in O, k. This results in a total time complexity of O, n plus u asterisk log u plus k, with space complexity remaining at O, n. However, the heap-based approach avoids the overhead of sorting all elements. By maintaining only the top k elements in a heap, it achieves a faster total time complexity of O, n asterisk log k, when k is much smaller than u, while still maintaining the same O, n, space complexity. For a deeper understanding, we consider the best, average, and worst-case scenarios. In the best case, where all elements in the input are identical, the number of unique elements is minimal. Here, the time complexity is dominated by the counting step, resulting in O, n. For the average case, where the number of unique elements is moderate, the time complexity is O, n asterisk log k. Finally, in the worst case, where all elements are unique, the time complexity remains O, n asterisk log k. To mathematically validate this, we observe that the dominant term in the heap-based approach is u asterisk log k, where u is at most n. Since k is smaller than n, the logarithmic term grows slower than any linear term. As a result, the time complexity scales as O, n asterisk log k, while the space complexity remains O, n, confirming the efficiency of our solution. When solving the top k frequent elements problem, there are several common mistakes to avoid. First, it's important to use an efficient data structure for counting frequencies. Many beginners make the mistake of using nested loops, which results in a time complexity of O, n squared. Instead, leveraging a hash map allows you to count frequencies in linear time, or O, n. Another common error is sorting the entire list of elements unnecessarily. Sorting all elements by frequency takes O, n log n, time, which is often excessive. A better approach is to use a heap or bucket sort to directly find the top k elements, which reduces the complexity to O, n log k, or even O, n, in some cases. Additionally, you should consider input size constraints. Large inputs require careful memory management because creating large arrays, such as in bucket sort, without validating the input size can lead to inefficiencies or crashes. Finally, watch out for off-by-one errors when working with heaps. Remember that Python's heap is a min-heap by default, so you need to ensure that the logic for pushing and popping elements maintains the correct heap size, which should always remain exactly k. Another mistake to avoid is overcomplicating the process of selecting the top k elements. For example, some solutions involve iterating through the heap after extracting the top k, which is redundant. Instead, you should adjust your logic to directly extract or store only the top k during processing. Now, in interviews, it's crucial to not only solve the problem but also to clearly communicate your choices. Be prepared to discuss the trade-offs of your approach, such as why you chose a heap versus bucket sort, and explain the time and space complexities of your solution. Additionally, always consider edge cases. For instance, what happens if the input is empty, or if k is larger than the number of elements? How does your solution handle cases where all elements have the same frequency? Another key point to highlight is optimizing your solution based on the value of k. Small values of k make heaps particularly efficient, while for larger values of k, bucket sort might be the better choice. Finally, hash maps are a pivotal part of this problem for frequency counting. Be ready to justify their use, and if the inputs are restricted to integers, you can even discuss alternatives like counting sort. If you're looking to expand your understanding of related problems, there are several you might find interesting. For instance, LeetCode 692, which focuses on finding the top k frequent words, offers a similar challenge but with strings instead of integers. Then there's LeetCode 973, which asks for the k closest points to the origin, presenting a geometric twist to the idea of prioritizing elements. Of course, the original problem, LeetCode 347, remains a foundational one. Another variation is LeetCode 451, where the goal is to sort characters by frequency, which involves a slightly different output format but shares similar computational principles. Now, in terms of alternative approaches to solving these problems, the heap-based method is a strong option. It's particularly efficient when k is small, as it operates in n log k time. The min-heap ensures that you always retain the top k most frequent elements. However, it becomes less efficient as k approaches n. In contrast, bucket sort offers a linear time complexity of n for frequency counting and sorting, which makes it an excellent choice for large datasets. That said, it does require additional space proportional to the frequency range, and for inputs with extremely large ranges, this can become a limitation. Another approach worth mentioning is quick select. This method is particularly powerful for finding the top k elements in datasets that are very large, as its expected time complexity is n. However, it's important to note that its performance can degrade to n squared in the worst case, especially if the pivot selection is poor. This makes it a bit riskier to implement under time pressure, such as during an interview. On the other hand, a sorting-based approach is the simplest to implement. It's intuitive and straightforward, but it falls short in terms of efficiency when dealing with large datasets, as its time complexity is n log n. This makes it less favorable compared to heaps or bucket sort. Ultimately, the choice of approach depends on the constraints of the problem and the size of the dataset. Each method has its own strengths and weaknesses, and understanding these trade-offs is key to selecting the right solution for a given scenario. Great job! We've successfully tackled problem number 347, top k frequent elements. To summarize, we've seen how to use hash maps for frequency counting in heaps for efficient retrieval. These are powerful tools for solving similar problems. Keep practicing, and don't forget to like, share, and subscribe for more content. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!